Hello, I'm Rick Schildhouse, and I've gotten asked several questions by numerous people about types of railroad track for model railroading, types of transformers, types of rolling stock, whatever else. So this is one of several videos that I'm going to address those issues in. And it comes up because we get transformers that look like this, pretty small guys, pretty light. And put that guy over there. We get transformers that look like this, fairly light. We get behemoths like this, which are annoyingly heavy. That's a Lionel. And we have track like this with 2 rails. And we have track like this with 3 rails. Obviously, gauge distance between track is an issue. And then we have track like this and track like this. So in this video, I am going to address power supplies, types of power, and why the track sometimes has 3 rails and sometimes has 2, and it has nothing to do with the size of the rolling stock. So let's get on with it. Hope you enjoy it. When we talk about powering up model railroading, the thing that we need to work with is transformers. And I'm going to show you some of the differences between the AC and DC powered transformers as you shift from scale N, HO, OS, O, G. So here is one of my N scale transformers. It's the little guys, and it weighs a whopping 13, almost 14 ounces. And when we step over to the HO transformer, this transformer weighs a whopping 1 pound 2 ounces, 18 ounces. When we step over to the S scale transformer, we're getting a little bit heavier. This is also called the American scale transformer by some people. We're talking about 1 pound, almost 12 ounces, so we're talking almost 28 ounces. When we step over to the O gauge transformer, commonly called the Lionel transformer in the US, we're talking 3 pounds 10 ounces, almost 3 pounds 11 ounces. So we're talking almost 59 ounces in this. And this is actually a Verivac. The others are DC, AC line power from the wall to DC power. This one is AC power to AC power. It's called a Verivac. And the last one we're going to look at is the one from G scale from the Aristocrat. And this is also a DC system. And we're down to 2 pounds 1 ounces. We're down to 33 ounces. So the type of transformer you have, AC or DC, not only affects the power output, but the power type. And when you talk about AC power out, that's a Verivac. It's a complex system. It's very heavy in weight, very high in cost, in relation to a DC system commonly used in the N scale, HO, S, and G scales, which are fairly light, fairly inexpensive, easy. AC in, DC out, easy, cheap, generally light. AC in, AC out, fairly expensive, very heavy. And let's step on to the next element. In powering model railroads, the next thing we're going to talk about is track. And there's 2 terms in model railroading that get interchanged, and it's quote-unquote inappropriate to interchange them, but it really doesn't matter. Gauge is the distance between the 2 tracks, and scale is the size of the rolling stock in relation to the prototype or the realistic model. It doesn't matter if you say I'm running HO scale, that means you've got HO track. You can't put HO on HO rolling stock on S scale track. It doesn't matter. In this photo, that ruler is 6 inches long for a reference, and starting from the bottom and going up, it's N scale, which is the smallest. Then it's HO. Then it's S, also called American Flyer scale. Then it is O, also called Lionel scale. And then it is G scale. So when you take a look at these in relation to each other, and I'm going to set up the photos so that you can see them, we have G scale up against O scale, so you can see how the difference in the gauge sets up. And then we have O scale to S scale, American Flyer scale, and how it sets up. And then we have S scale to HO scale and how its relationship is. And then we have HO to N. And this is a system that we're working with. If we go back and look at the track array picture, the only one that is 3-rail is the O, or the Lionel scale. And that is the only one that we're going to power in my system with AC. Everything else is DC, and we're going to discuss why and the advantages and disadvantages besides the transformer issues that we've just discussed. This is the 2-rail system that is common to N, HO, S, and G scale, and it's DC powered normally. In every instance I've ever seen, it's DC powered. So one rail is positive, the other rail is negative. To reverse the direction of the train, you flip the polarity. The positive becomes negative, the negative becomes positive, the engine goes, the train goes the other direction. A very simple system, and this is normally the layout you get with your beginning set. And there is not a problem here. Polarity always remains the same, there's not interference. This is the 3-rail system for O gauge or Lionel gauge. It's the AC system with that, and my colors are backwards, I'm sorry. The center rail is normally considered the hot rail. Alternating current has hot and neutral. DC current, direct current, has positive and negative, and that's because the cycles with AC change the polarity. With the basic Lionel set coming as a basic oval, the center rail is considered to be the hot rail. The 2 outer rails are considered to be neutrals. And to change the direction of the engine, you go to the transformer, the Varivac. You do some interesting things inside the Varivac electronically, and then it sends a signal to the locomotive. The locomotive does something internally with its little gizmos, and the train goes backwards. It's not simply changing the polarity, because the hot rail is always the hot rail. The outer rails are always the neutral rails, and this is why the Varivac is used with Lionel. Lionel operates the AC and requires the 3-rail system. But it works really well. This is where 2-rail DC runs into issues, and that is because we have to maintain isolated polarity or isolated distances electrically between the rails. As we had with the basic oval, the outer rail was red and stayed red. I'm going to call it positive, and the inner rail was negative. It was black. I'm going to stick with that. When you start adding figure 8 patterns, crossovers into this, as you look from the left side, the outer rail goes from the lower left to the upper right and connects to the inner rail. And what happens is, this is a direct short. Now the positive from the outer is connected directly to the negative of the inner, the direct short. Your transformer shorts out, blows a fuse, pops a circuit breaker, whatever it does for circuit protection. The correlation of that is also that the inner rail, going from the upper left, comes across down and connects directly to the outer rail. So you've not only got one short circuit, you've got 2. And you actually have 4 or 8 as you go across this. Because of this, when you get into complex construction issues with DC, you have to use an insulator to isolate those track sections electrically, and then you have to use switches to control their polarity, and those switches are going to be double pole, double throw switches. So you flip them, and when you flip it one way, one rail is positive, the other is negative. When you flip it the other way, it reverses. The first rail went from positive to negative. The second rail went from negative to positive. Otherwise, what happens if you don't flip it, if you insert it with the insulators, but do not set up so that you can change the the polarity. What could happen is the engine could come across, hit that, and we'll show you in the pickups on the engine, and the engine is sitting in two sections, one where it's getting positive current on one wheel, negative current on the other pickup wheel, creating a short by itself, and the engine shorts out. Because of that, DC two-rail system starts getting complex when you start making complicated or intricate layouts like this. So you end up putting in blocks, electrically controlled blocks. You end up putting in switches, and you have a lot of fun with it. It's great to make these, but it's complex, and it's not for the beginning 10-year-old kid. This is where the advantage of the three-rail AC system wins out hands down. 5-year-old kid can put this together. It never shorts out. It never shorts out, and we'll show you in a little better detail how this works. It never shorts out because the inner rail is always kept electrically isolated from the outer rails. The hot rail, the inner rail, is always kept isolated from the neutral rails, the outer rails. No matter where you go, how you go, set up the issue as complex as you want it. It does not matter. It's not going to short out on you because of its design. But you pay for that convenience. You pay for a higher cost Varivac, you pay for higher cost engines, you pay for a higher cost track. But the layouts are very, very convenient. Just put down the rails, snap them together, put the train on them, hook up the wires, plug in transformer, and run them as complex as you want. Super system. Really appreciate it, and quite honestly, I go for AC and DC. I go for DC because of its scales. I go for AC because of its convenience. Super system. Let's show you a little bit better in detail. The first thing we need to understand is how the Lionel O scale picks up its electricity. This is the bottom of my F7 Lionel, which you saw earlier. It's a monstrous beast. Those two rollers between the wheels on each carriage, one roller on each carriage, is what contacts the center rail. And then the actual railroad wheels, as you would call them, contact the outer rails, and the electrical flow comes in from the hot rails to center contacts through the control mechanism, through the motors. This engine has both trucks, what are called trucks or carriages, powered, and then flows out through the neutral rails, even though it alternates all the time. You consider it as constant flow. This engine is a early 1950s construction. It's been through a number of floods. I've repaired it a number of times. It still runs. I wish it were in better shape. It's not. It's been used and abused, and I absolutely love it, and I'll keep it forever. But the issue is those center rollers are going to create a problem for us, and that is when it crosses over those switches, and I'm going to show you the switches and explain the problem that develops. Here's a photo of what is technically called a turnout, and inside a turnout is a switch. The switch is the parts that move. The turnout is the entire assembly. I use turnout and switch interchangeably. Don't jump on me. I'm sorry. I do not have all of the electrical isolation elements depicted in this. But here's where the problem comes up. If the engine is going from left to right, straight through the turnout, what happens is that rail that goes from the outer track near the bottom center to the outer track on the turnout, as if the train were to make the turn, would short out if that center section, if the outer rail for the turn was always neutral. So what happens is Lionel has put a number of isolation points in here, and underneath the switch is a bunch of movable contacts. As the switch goes from straight through to turnout, what happens is different elements of this track receive different signals. Sometimes they receive the signal that will make them a neutral, sometimes they receive a signal that will make them a hot, and that always prevents the engine from shorting out as it travels over this turnout. This is a complex gizmo, and it's why a turnout for an HO track or an S gauge track would cost you, say, $10, and this will cost you $25, because this has got a whole bunch of stuff underneath it. Plus, this is electrically controlled. This is on my layout, and I have threads holding the little lamp. The lamp indicates whether it's going to be a straight through or turnout on this turnout. It's kind of cool. But we have to figure out a way to electrically isolate and change the various components of this turnout from being hot to neutral, or from neutral to hot, depending on whether the engine is going to roll straight through it, or it's going to take the turn and curve out of the straight through track. And it's done miraculously. It stops the shorts, whatever. It works really well. This is what complicates AC in a layout, and this is why AC as a layout is more expensive. This is the undercarriage of my HO Jeep 7 GP7 Tyco. Notice no center wheels on the carriages. The front truck, the truck on the right, picks up from one rail. The truck on the left picks up from the other rail. And this is how this system works. It stays that way. There is no issue about violating the electrical isolation issues when you cross over a switch. That can't be easily handled, and I'm going to show you an HO switch here in a second. So here's a HO turnout, correct term, and a whole lot simpler. This is currently set up for straight through, and as the trucks go through, pick up their contacts, there's no shortage issue. You do see a couple of isolation issues where the tracks kind of interact, and that is the justification for having two wheels on each truck being electrical pickups, because as one wheel rolls over that plastic isolation towards the right lower rail, the other truck will still be receiving electrical flow, and it'll continue to move through without an issue. If you flip this so that its train is going to take the turnout, there is not an issue with the inner rail interacting with the outer rail, whatever. There's no center rail to interfere with this. Super simple switch. Works really well. That's why it's inexpensive. However, it requires electrical blocks, and that just makes construction a little more interesting. On YouTube, I have a video of a Hogwarts Express layout, Lionel Hogwarts Express layout that I made for my wife, and it goes from rolling to up and running in less than 3 minutes. An error I made in making the video: you should clean your track before you make a video like this. My track was dirty, so I had some problems getting the rolling stock to roll, and I also didn't get the carriages, the wheels in the track right the first time, and those are the only items that slowed me down. It's fun to watch. Enjoy it, and enjoy the video, and good luck with model railroading.